Hello, good morning, everyone. Today, inshallah, first of all, happy Eid, and I'm really very happy to be with you today. Today, I would like to talk with you about parametric shapes and parametric representation. I'm sorry to record this lecture so rapidly because the last period we our step was a little bit slow because of Ramadan كل سنة وانتم طيبين and because of the Eid vacation. So we had to catch up as fast as possible, especially that our midterm it will be around the corner, as you know from our previous lectures. Uh, I uh, uh, I dedicate this lecture for you all. This lecture is gonna be about parametric representation, as you will see, and it's really a very nice topic. It's not difficult, but it needs a good understanding as an introduction. You will have a series of slides and recorded lectures that I can upload quickly on the YouTube, but I thought this one it will be better to be just between a talk between me and you. You can watch it while you are relaxing through this vacation, but please try to go through it. It's really very important. It will help you out to catch up as fast as possible. And once more, I'm sorry for just recording in a very short notice. And I know you are enjoying your vacation at the time being, but just if you could skip just 30 minutes or so, just going through this lecture, and I will try to make it as short as possible, inshallah. Thank you very much for attending and watching. Okay, I will start with why we are studying parametric curves and why it is really very important. This question is important for you to understand at the beginning of our lecture today. Why we use parametric representation of functions. We need parametric representation of functions to make our life easier, especially if we are dealing with Cartesian or with equations in Cartesian coordinates or in any other coordinates. If you remember in the previous lectures, we took Cartesian coordinates, spherical coordinates, and cylindrical coordinates. And we knew that in some cases, with some shapes or surfaces, it is better to deal with them using cylindrical coordinates, like paraboloids, for example, or using spherical coordinates, which is really very helpful if you are working with or talking with a sphere or something, or even in the two dimension using a polar representation, which is r and theta, which a way makes your life easier if you are integrating or doing any other mathematical evaluation or something other than using the Cartesian coordinates. For example, for a circle or something in Cartesian in two dimension, it's x squared plus y squared equal 4. While in using polar, for example, it's going to be r equal to 2. This is why we are changing and choosing the suitable type of coordinate systems that we use. From this point, it comes our hero, which is the parametric representation of curves and surfaces. As you see from according to this of lines, it provides more flexibility and control when you are describing a curve and the surface, especially in the cases when standard Cartesian coordinates become complicated. So it's just enough just to imagine instead of dealing with x and y, you are dealing with one variable which is t. Instead of dealing with x, y, and z, you are just working with just only one parameter, which is t, as you can see. So this is really very important. So if I started by describing complex curves, as I told you, some curves like circles or spirals can't be easily represented. This is what I've just explained to you in the previous slide. From, as you can see, of x in the form of y as a function of x. This is really a very good example considering this circle. For x squared plus y squared equal r squared, it's a difficult to express as a single function, the y is equal to f of x. Once you try to do so, it's going to be y equal to the square root of r square minus x square. And if you are taking the root, it's going to be about positive or negative. While if you are using parametric representation, it's going to be x equal to r cosine t and y is r sine t, where t running from 0 to 2 pi. So instead of dealing with x squared plus y squared equal to 4, I'm just using x equal to r cosine t and y equal to r sine t. And while t, of course, here represent an angle, and this is, I will take this a chance and tell you that t is not always going to play the role of a theta. In this particular example, t is playing the role of a theta, so it's moving from 0 up to 2 pi. In other problems or in other applications, we will see that it's just a range from -2 to +2 or from -1 to +1. But instead of dealing with two variables x and y, I've succeeded of getting a variable just only as t. So x is a function in t, y is a function in t. So instead of dealing with two variables, I'm dealing with just only one variable. How the points of the circle is going to be drawn, it's really very important, and also it's very simple. If you remark, when t is equal to 0, so I'm talking about this line. If you make a substitution in this equation, it's going to be x equal to 2 cosine t and y is equal to 2 sine t, since the circle is about x squared plus y squared equal to 4. So if you use t is equal to 0, that's the main I will usually use in case of t equal to corresponds to an angles. I will use the main angles, which are 0, pi over 2, pi, 3 pi over 2, and 2 pi, just to give you a hint about the points. So if I used t equal to 0, all I have to do is to make the substitution. So x is going to equal to 2 times cosine 0. Cosine 0 is 1. 1 times 2 is 2. So in the x direction, the length is 2. While in the y direction, r sine t, which is 2 times 0, which is 0. So actually, it is the point 2 and 0, this point. If you use t equal to 90 and make a substitution, cosine t will give you 0 at 90, while sine t is going to give you 1. So it's a 2 times 1, and this guy is 0. So I'm at the point 0 and 2 in xy. So once more, this is going to be the point. Then also, to continue, if I'm using the angle negative y and I'm making the substitution, I will be ending up with the point -2 and 0, which is this point, and so on. Bottom line, the idea of the parametric is it is just trying to make a trajectory, putting points beside each other and starting from t equal to 0, and those points are increasing. One of them is sine, and this is the x value, and that's the y value. That's the x value and the y value. Also, that's the x value and the y value for all of these points, and so it will represent a circle. So that's the main key or the main thing that we rely on while we are using parametric representation. It's really very smart an idea, and it's like making an assumption that x equals certain value and y equal to certain value, and they will all, both of them work together in order to make these points coming true. Once more, for the parametric curve, let I is a subset of R be an interval, and let F and G are such that they are from I into R, be two continuous function. The function x and y, this is exactly what I was telling you about, is about f of t and g of t. So the points x and y are represented by f of t and g of t. Another thing, just to put in mind, so the circle that we were talking about, which is x squared plus y squared equal to 4, it can be written in the relation between x, y, and the t value as 2 cosine t and t sine t. Those are the corresponding values for x and y. And this is how we call it a parametric curve in R2 or in the plan, as you can see. In the 3 dimension, it's just a generalization of this idea. So it's exactly the same, but just only a generalization of this idea. So if I was in the 3 dimension, instead of having just only 2 components in x and y, I will have the 3 components in x direction, y direction, and z direction. So given 3 continuous functions, g and h, and such that from I into R, if I'm talking about the 3 dimension x, y, and z, I will have a function in t representing x, a function in t representing y, and a function in t representing z. I'm sorry, that's a typo. That's an x, y, and z. I'm sorry. So t belongs to the interval, as you can see, and it's called a parametric curve in R3. For example, let's see these problems. And by the idea, through our lectures, I'm trying to break, as you saw in the previous lectures, I'm trying to break the sheet and the problems into more exercises, as you will see in this session. And there will be more exercises in the coming sessions. This is why I've spread the content on multiple videos, because each one or each part of these videos, I will try to cover a part of the theoretical and the practical both together in one video, as you would see. Geometric representation for parametric curves in R2. Let's see the first one, which is cosine t and sine t, where t is greater than or equal to 0 and less than or equal to 2 pi. By try and error, and by trying these curves, you will have the experience to know what's going to represent. So if I'm using this guy, which is cosine t sine t, while t is greater than or equal to 0 and less than or equal to 2 pi, this is mainly is gonna be a circle. So those are the cosine t and sine t, and this is t greater than or equal to 0, less than or equal to 2 pi, and that's the shape of the circle. It's a unit circle. As you can see, if I put something, a constant here, so if it is 2 cosine t, 2 sine t, it's going to be a circle, but with radius 2. If I put r cosine t, r sine t, it's going to be a circle with radius r. If r is equal to 1, like this case, it's going to be a circle, as you can see, with radius equal to 1. In a similar manner, if I want to draw cosine t plus 2 sine t, not just sine t to cosine t, I take the advantage in order to make you see this problem. As you can see, the radius is not the same in the x direction and in the y direction. And we have something we talked previously by the beginning of our lectures, where you have a circle. Now, if you have multiple radiuses, then you will have an ellipse, which is an equation of an ellipse. And it makes complete sense. Once more, those two guys are x and y. Just to change the value of t from 0 up to 2 pi, and you will have your points beside each other, and you will be able to graph this ellipse. So for example, if I inserted t equal to 0, this is going to be cosine 0, which is 1, while 2 sine 0, which is 0. So I'm talking about 0 and 1. If I'm using the t equal to 90, so cosine t is going to be 0, while in the y direction you will have 2. This is why the radius here, or the semi-minor radius, is 1, while the semi-major x is in the y direction and is equal to 2, and it will continue according to the values of the angles starting from 0, 90, 180, 270, and then 360, as you can see. This is also another shape of a part of an ellipse. Remark that I'm controlling the value of t to be, instead of from 0 up to 2 pi, from 0 up to pi. So all I did here, just replacing the values, x will be sine t and y will be 2 cosine t, and that's the shape that we will have a half of, or a semi ellipse, as you can see, and it is elongated on the y-axis. Also, that's gonna be a very smart shape. It's coming from t from 0 up to 1.5 pi, okay, or 1.5 times 180 if you are using degrees. And that's the shape of a part of three quarters of an ellipse on this shape. Bottom line, what I want you to keep in mind, all I have to do, use main angles just to speculate the shape from 0 pi over 2 pi, 3 pi over 2 pi, blah, 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 and get the corresponding point. So if I'm using 0, I'm talking about a unit circle. If I'm using 0, you will get 1 and 0. If I'm using 90, you will get 0 and 1. If you are using 3 pi, it's going to be negative 1 and 0. And so on. Those are the points, the 5 points around the shape of your circle with the main angles 0 pi over 2 pi, 3 pi over 2 pi, and so on. That's the simplest thing that you can do or you can imagine. Type. What if I'm talking about the three dimension? A similar discussion will be the same. It's going to be exactly the same. So, and as I told you previously, it doesn't have to be just only angles. It may be numbers or whatever. So here in the first function, it represents, or the first mathematical expression, it's an x, y, and z, while x is equal to 3t plus 2, and y it's equal to 8t minus 1, and z which is equal to t, where t is changing from negative infinity up to positive infinity. And this is something really very nice. I will try to get just only around the corner between -1 and +1 and see what's this linear or multilinear equations will lead me. But remember, we are in the X, Y, and Z. In the X, Y, and Z, I hope the cam is getting my hand. I'm talking about the X axis, Y axis, and the Z axis. Okay, so once we try to do so, all I have to do is to substitute, let's say, with -1 and +1. So inserting a -1 here, it's going to be -3 plus 2, which is coming to -1. -1 here is going to be -9 and the -1. That's location of a point in the three dimension. If I change it to +1, I will have another point. If you try to draw it, I hope it is clear to you on this three-dimension coordinates. This is the x-axis, y-axis, positive z-axis, and that's our equation. If you can see, I'm trying to get more closer to the screen as I'm talking to you, which represent a straight line, as you can see. It's coming from the negative side to the positive octane of this space. So if you look also to problem number B, this is really very interesting. If I took from just -40 to +40, just to make it to just to be able to represent this idea, I'm making the substitutions of cosine t, sine t, and t for each one of them. This is stand for the x, the y, and z, which are going to be points beside each other. The connection or the while you are connecting all these 2 points all together, it will give you the proposed shape. It's gonna be the shape of a spiral. If you can see in the three dimension around the z-axis, as you can see. I want you to imagine dealing with these applications or with these shapes in the three dimension, or you are trying to have an application for evaluating a velocity of a particle moving on this spiral shape, or a strong body just moving around its shapes or whatever. And imagine how it is gonna be very difficult to deal with, while it's going to be much, much easier to deal with if you are using uh, 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 co- uh, normal coordinates like, I'm sorry, parametric coordinates like t in this case. It's going to be much easier, as you can see. Once more, The parametric curves or oriented lines or curves, this is a continuation of our topic. And in this part, we will go step by step to the vector valued function. This is really very interesting an introduction to this topic of functions, but represented in the parametric form. I can see I can say that it's really very successful entrance for this topic or approaching or a way in approaching this topic. So parametric curve in space is represented geometrically by a line or oriented curve C, drawn by the points x, y, and z, where x is a function in t, y is a function in t, and z is a function in t, where t varies incrementally in the interval I, while t is changing as you can see. We say that C, the curve oriented, is increasing direction of the parameter t. So C by itself, this curve, will it change according to the direction of the parameter. Parametric curve in space can be thought of as the trajectory, as I told you, as a trajectory of a particle moving in space at which time t is at point. So in order to get the points near each other, you know that x as a function of t, y as a function of t, and z as a function of t, as you can. The parametric curves or vector functions, when studying parametric curves in the plan, it is convenient to identify the point xy as f of t and g of t, and I can write it as a vector function using the canonical form of the two dimension. So I can say that R, which is a vector function. It's f of t in the direction of I, and g of t is the direction of g. It's like exactly say that this function, it is represented by f of t in the x and g of t in the y, for example. Of course, I and j represent the canonical of R2 or the main reference as we talked previously in linear algebra. And I'm sorry, I have to say that as you can see, we cannot live without linear algebra or survive without the knowledge of linear algebra, which is involved in almost everything. So once more, if I am in the space f, x, y, and z, similar definition. So R as a vector valued function in the three dimension, it's gonna be f of t in the direction of I, g of t in the direction of j, and h of t in the direction of k, which stand for the x, y, and z components of this function. Those are the canonical of R3 as you can see. So a vector function R of one variable with values in R2 or R3 is a correspondence which associates a single vector of R2 or of R3 to each number in a given subset. D is a subset of R, which is called the domain, of course, which is controlling the values of these functions. So for every t belongs to the domain of your vector function, it is written as a linear combination of elements of the basis I and j. So R of t is f of t in the direction of I plus g of t in the direction of g. And a similar discussion for three dimension is going to be f g f in the direction of I g k correspondingly. And so those are they are called the components of t is called the parameter of the vector value function as you can see. The domain of functions is the regular one. It is the natural domain. It's considered where the three functions f of t, g of t, and h of t. So I'm raising my head in order for you to see. So it is the natural domain where f of t, g of t, h of t can work all together. I will take this advantage and give you an example just to make you see how we can find the domain in the case of real valued functions or the functions in several variables, which are x, y, and z, and the output is in the three direction I, j, and k, as you can see. All I have to do is to determine the conditions of t that will work for the three components at the same time. So which means for the I direction, which is cosine t, I have no regulation. So all the real numbers can work with cosine function. So the function cosine t is defined for all values of t. So the domain, we have no regulation on t. But for the logarithmic part, log 4 minus t, the logarithmic part, its argument, which is 4 minus t, must be greater than 0, which will give you uh, 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 which will give a limitation for the domain that if you move negative t to the other direction, I will have a limitation on the value of t that it must be t less than 4. So according to this condition, the first component, second component should be fine for having t less than 4. The first has nothing, it's okay with it for any value. And for the second, that's the condition to make it defined. We will go for the third one or for the third condition, which the square root must be also obeyed, which means that t plus 1 must be greater than or equal to 0. That's t is greater than or equal to negative 1. So I have two limitations, that t must be less than 4 and the t must be greater than or equal to negative 1. So this is the value of t which will have to satisfy these two conditions in order to have a logical expression for x, y, and z, as you can see. So according to all of this, this is gonna be the value of t, which is greater than or equal negative 1 and less than 4, as you can see. That's the domain of this real valued function as explained. طيب, if I try to push a little bit and going through the limit in the case of the parametric representation of curves or surfaces, and once more, within the next lectures, we will have more examples on the very famous shapes. I believe I inserted this part in the coming video and in the coming set of slides in order to make your life easier in speculating the shape or the surface that you can face. I believe I did go through this within the next lecture, inshallah. So the limit for a valued function, it's exactly like the limit, but it's in one dimension, but it is generalized, or the limit of several variables, functions in several variables, but it was generalized. So the limit of t tends to t node for vector function or of t, it's gonna equal to the vector b. How it's gonna be done like this is gonna be simply taking the limit for the first component, second component, and third component for t tends to t node. And then I will get the value of r of t regarding the value of the vector valued function at the corresponding value of t node. Is continuous at the point t node. It's the same definition of continuity. As you know, we usually take the limits first, then we continue handle the continuity issue. It's exactly the same. Observation: a vector function is continuous at a point in its domain if and only if it's related to the definition of the continuity. Its component is continuous at that point, and the limit equal the definition of the function at that limit at that point, as you know. In this slide, we are in trying to, I've already said that previously, it's like trajectory. The use of x as a function in the x direction, y direction, and the z direction, it's like trajectorying the value of the function at certain points in the space. So let the subset of R be an interval, and the vector function, this is the x component, the y component, the z component, are continuous vector functions in I with values in R3. For each t belongs to I, we consider vector I with the initial point at the origin of the orthogonal reference frame, and then the point, the values of x, t, y, t, z, t, those are the points beside each other, and you will be able to get an orientation or representation of a line, of a curve, of a surface, whatever. When t varies in the interval, the tip of the vector rt describe an oriented line c in space, which is called the graph of a vector value function, as I've tried to explain to you. The line c corresponding to the graph of a vector, which is xt of I, yt of j, zt of k, coincide with the line previously denoted by the curve xt, yt, z of t extended for x, y, and z. Let I, the subset of R, be an interval x dot y dot z dot where I into R are differentiable function at the point. So uh, meaning that if we want to get the derivative of R, all I have to do is to get the derivative of the three components x, y, and z. As you can see, those are the derivatives with respect to t. Also, the definition or using the definition, it's exactly similar to what we have been trained on in one dimension, which r dash of t equal to the limit of h tends to 0, or the definition of r t plus h minus r of t divided by h. And this is for the first order derivative, and a similar discussion for higher order derivatives, it's exactly the same, which in common English, you can find the derivative or the vector function by deviating or getting the derivative of the components at I, j, and k, or for x, y, and z. The derivative of function is a vector function, of course. Once more, the derivative of a vector function is a vector function. Derivative rules are all applied, so, and with the multiplication rules and everything, so let R1 be a vector and R2 be vector functions in R2, or in R3, it's the same discussion. Differentiable on the interval I, where f is such that from I into R, differentiable on I, and let G be the interval differentiation on G, so if, which means the derivative can be distributed on the addition. So if I have two vector functions R1 and R2 and I'm differentiating, it will be the derivative of the first plus the derivative of the second. If I have two functions or a function multiplied in a vector valued function, then the derivative will be according to the addition rule. Get f of t times r dash, then f dash times r of t. If you have two vector valued multiplied or two vector functions multiplied in each other, so it's going to be the derivative of the first times the second plus derivative the second times the first, as usual. Even in cross multiplication, it will be with a cross multiplication exactly the same. And if you have a composite function, then the composition will be the differentiation of the outer function, okay, times the derivative of the inner function, as we will see with coming examples, inshallah. Also, the derivative of a vector function, geometric interpretation, it will give you the tangent. So this is here, if h is greater than 0, this is r of t, and that's r of t plus h. This is the limit that we are taking, which is rt plus h minus r of t, while h tends to 0, and that's in the case of h greater than 0, which will give you the tangent, which is r dash at a certain point. So the tangent vector to a parametric curve, if I have the vector valued function, if I have my vector function and I differentiate it, I will get the direction of the tangent at this point. So let's see be a graph of a vector function r, differentiable at point t node. Suppose that if r dash doesn't equal to 0, it has an initial point on the point of the vector, which is t node, then the vector r dash is tangent to the graph of r, as I told you at the point in the increasing direction of t, as you can see. Now I will have some problems from sheet number 3 in order to make your in order to make you familiar with the types of the problems that we will have in this part. So in this part, he wants you to represent geometrically the curves 2t plus 1 and t square, and also the curve sine t cosine t minus 3, while t is from 0 up to 2 pi, and this is the given the value of the function of the first curve. So if I started with 0, 1, and 2 and trying to substitute in this in the first set or in the first vector function, it will give you the given parabola. So if I'm using t equal to 0, let's start with 0. If you put insert t equal to 0, you will have 1 and 0. which is the vertex of your parabola. If you start increasing the numbers on the side, you will start having the shape of the parabola as you can see. Also, it's a very good idea at the time being to use a parametric grapher on the internet. I believe Dismos is really very nice program to use in order at the time being to make you speculate the shape or to imagine the shape of the curve that you are dealing with. So once more, if I want to get r of t, it's going to be really very simple. R of t is going to equal to 2t plus 1 in the direction of I and t squared in the direction of j. So it's a 2t plus 1 in I and the t squared j in the direction t squared in the direction of g. That's the representation of the first function, but in vector form. If I get the first derivative, I will be able to get the velocity. If I'm getting the second derivative, so I'm going to be able, or I will be able to get the acceleration. So just simply differentiate according to the derivative rules. 2t plus 1, if you try to differentiate, it's going to be 2. T squared, it's going to be 2t. So that's r dash, which is going to be 2 in the direction of I, 2t in the direction of j, as you can see. And that's r double dash, which is 2j if you are different getting the second derivative. So the first component is 0, while the second component is 2j, as you can see. If I'm using the second equation, which is sine t cosine t minus 3, and the t is ranging from 0 and less than or equal to 2 pi, all I have to do is to start substituting with the values. So I will have sine t in the direction of I, cosine t minus 3 in the direction of j, and in a similar manner, I will try to use the values between 0 and 2 pi and substitute in r. So it's going to be 0. Then if I use cosine t and the negative 3, I will be able to see the shape. It's going to be the shape of a circle, but with center away from the origin. It's going to be between 2 and negative 4, as you can see. So if I want to get r dash, it's going to be really very simple. All I have to do is to differentiate the component. So it's going to be cosine t, then negative sine t, as you can see for r dash. And for the r double dash, or the second derivative, it's going to be differentiating cosine t, which is going to be negative sine t in the direction of I, and negative cosine t in the direction of j. So actually, finding the first derivative and the second derivative, it's really very simple, usually we do. For more problems in this list, he wants you to represent geometrically the following parametric curves in R3 and determine the velocity and the acceleration. But in this case, I'm not talking in 2D, I'm talking in the 3 dimension, exactly the same. So if I'm talking about 2 sine t, 4 cosine t, and t is equal to 1, that means the z is going to be the plan at z equal to z. And for 2 sine t and 4 cosine t, that's an equation of a parabola. I'm sorry, of an ellipse. I'm really very sorry. So once more, this is r2 sine t in I and the 4 cosine t in j and k. So if I want to differentiate once more, it's gonna be 2 cosine t plus negative 4 over sine t in the direction of j and 0, as you can see. Differentiating more, this is gonna be r double dash. So once more differentiating 2 cosine t, it's gonna be negative 2 sine t, and negative 4 sine t, it's gonna be negative 4 cosine t and 0 in the t direction. And that's the shape that we are talking about. As I told you, this is x, y, and z, and that's at z equal to 1. It's a representation of an ellipse. If I moved further for this equation, which is cosine t sine t over 2 pi, it's gonna be a spiral, but in 3 dimension. Once more, this is r. If I want to get r dash, all I have to do is to just get the derivative of the 3 components in the x, y, and z. If I want to get the acceleration, I will do a second derivative for all the components once more. So it's gonna come up to negative cosine t in the direction of I minus sine t in j and 0 in k. And that's the shape that we are talking about. It's a spiral in 3 dimensions. I believe in this slides too, I've made uh, uh, another problem from the sheet, which is about computing the velocity and acceleration vectors for all t. And he wants you here, I've added another uh, request to find the equation of the tangent. If you remember in the previous slides, we spoke about how to represent an equation of a tangent straight line and an equation of a plane also. But in this case, I will be able to get the equation of a straight line tangent really very easily. So I will start with the first one. It's sine 3t cosine 3t to t3 over 2, which is a part of a spiral, as you can see, while t is equal to 1. So this is r. All I have to do is to get r dash, and that's going to be the direction of the tangent, and at the time t. So all I have to do is to start differentiating. So differentiating sine 3t is going to be cosine 3t times 3. Differentiating cosine 3t is going to be negative sine 3t times 3. Differentiating 2 of t to the power of 3 over 2 is going to be 2 times 3 over 2t to the power of half, as you can see. This is r dash, which are in the direction of I, j, and k, and that's r dash. Okay, once more, he wants you to get the acceleration, so I will get r double dash, so differentiating the three components once more in the direction of I, j, and k. So I will end up having negative 9 sine 3t, and this guy is going to be negative 9 cosine 3t, and that guy will equal to 3 over t to the power of negative half. As you can see, that's r double dash. Now, if I want to get the equation of the tangent line at t is equal to 1, it's going to be very, very simple. It's going to be x, y, and z equal the point plus lambda times the direction ratio of your curve. So the point, I will have to use the value of t at r, which is going to be sine 3, cosine 3, and 2, and that's the point. And for the direction ratio of this straight line, I will use r dash, but inserting t is equal to 1 at this point, and that's the direction ratio. So it's going to be 3 cosine 3, negative 3 sine 3, and 3, as you can see. So that's the point, and that's the direction ratio. Now I can write the line in its parametric equation, which is going to be x, y, and z equal to, that's the point, plus lambda times, that's the direction ratio. And I can also share it as x, y, and z. This is the first component, second component, and third component. In a similar debate, he wants you to compute the velocity and the acceleration vector of all t and define the equation of the tangent line at the specified value of t. And you have another problem, which is going to be also exactly the same. This is r t sine t, t cosine t, and root 3. This is r dash, exactly the same, differentiating the three components with respect to t, and that's the acceleration, exactly the same, differentiating the second time, or getting the second derivative for each one of them. Now I have r dash and r double dash. If I want to get the equation at t equal to 0, all I have to do is to insert equal to 0 in the first one. So I will be talking about a point, the origin. And if I make the substitution with e dash to get the direction ratio, it's going to be 0, 1, and root 3. So that's the equation of the parametric line, which is the point plus lambda times the direction ratio, as you can see, and then it will be simplified as you saw exactly. That's the line that we are talking about. So once more, it's really very simple, just to go through it step by step, and you will be able to get the equation of your line, as you can say, or tangent line. I believe this lengthy introduction about what's the parametric representation, what we are going to use with vector valued functions, which are functions in several variables with various outputs. It's really very important. Uh, I believe this is enough for today, and thank you very much for watching and following me. Please try to go through this lecture. It's really very simple. Summarizing everything, we need parametric representation to make our life easier. It's just like an assumption. for x, y, and z by the values of t. Once you do this, you will be able to get your function as vector function. If I want to evaluate the limit, the continuity, the derivative, it's going to be really very simple. And we had a minor application of getting a tangent on a curve just by making the steps of the last two examples. And that's enough for this session. I will add up more videos on the YouTube for you till we meet together next week, inshallah. Thank you very much, and with my best wishes for you all. Thank you. Bye bye.